So now we come to what I think it is in some sense the soul of RL, okay, the temporal difference methods, right. So I think TD is very important. So I mean you can argue that RL is all about learning from samples, learning to control dynamic complex system by just sampling from the system and so on and so forth, in which case like the Monte Carlo methods we talked about are also reinforcement learning methods, right. But for me, what is really cool about RL is the whole idea of temporal difference, okay. So what do temporal difference methods? There are many ways which I can motivate this. Did any of you hear me in Srinivas Chakravarti's class last semester? You did, but you don't count. Were you in Srinivas Chakravarti's class? Yeah, you were there, is it? I didn't even notice you in the class. You kept too quiet, or maybe you didn't show up that day. You did, huh? Okay. Anyway, so that was the only person. So, but you don't count. You are not taking the class for credit, are you? No. Okay. You don't count. But anyway, so I motivated in a very different way. Temporal difference I motivated in a very different way from a completely neuroscience, or not even neuroscience, more like a behavioral psychology point of view. Okay, so now I will do it purely from a computational point of view, right. So let us start off. So what did we do when we did dynamic programming, right. So one way of thinking about what we did with dynamic programming, you start with some state S, right, then you look at all possible outcomes, right, you look at all possible outcomes from that state, right. So what is, so this is all possible, let us say these are actions, right. So all possible actions I can take, and all possible outcomes from those actions, right. So what does this correspond to? My pi SA, right. So sum over A pi SA, so that is what this corresponds to. And what do these things correspond to? This much, yeah, sum over S prime P S prime S given S comma A, right. So this is essentially what I did when I did dynamic programming, right. So every time I did a backup, I took the entire possible outcome, right, and I looked at each one of the states here. I used the values of those states and did a backup, right. I did a backup. So this kind of backups are called full backups, right, and it is also distinguished by the fact that I am using the values here, right. This is called bootstrapping. I did a full backup and I did that using bootstrapping, okay. So next we looked at Monte Carlo methods. So what did we do in Monte Carlo methods? I started in a state, took some action, went to another state, took some other action, went to another state. I did this till I reached a terminal state. Then I used the rewards along the entire trajectory and updated the value of that state, right. So what did I do here? These are called sample backups, because I did not take the full possible set of outcomes, I just sampled an outcome, okay. I just sampled an outcome and I do not use any bootstrapping. So I do not use the value of this state to update the value of this state, right. Of course in the tree search thing we are talking about, we did use bootstrapping, but now we are not using any bootstrapping. The plain vanilla thing we do not use any no bootstrapping, correct. So what do you think I can do next? Huh? Bootstrap and sample, yeah. So I can do sample backups with bootstrap. Okay. And I will be extreme. That's all. It's one sample and I will bootstrap. Just like we did here, one sample, but we went all the way to the end, we did no bootstrap. So here what I will do, I will start from some state, I will take an action, I will look at the next outcome and use the value of this state to update the value of this state. Right. In a full backup, I do all of this and update. Here there is no simulation also involved, right? I am just using all possible outcomes. Well, here there is a simulation involved, here there is a simulation involved, but here it is only a one step simulation. I just use the value of this state to backup. Okay. So such methods are called temporal difference methods. Why are they called temporal difference?
Using a value at Tn to get an estimate at Tn plus 1.
Other way around. Use the value at t plus 1 to get an estimate of the value at t. Right. So essentially look at the prediction you make at time t plus 1, use that for changing the prediction you made at time t. Right. So look at the difference over time. So it is called temporal difference. You look at the difference in predictions over time, you call this a temporal difference prediction. Okay. Hey, that's a very pictorial motivation for why you want to do something like that. Okay, let's do a little bit more formal thing, right? So if you think about what we did with Monte Carlo methods is that I was interested in looking at that, right? But at every point of time I had some sample GT, okay, I did not have the expected value, I just had some value that I had sample, I had GT, right. So if I want to write this as a stochastic averaging method, right, so what will I do? I have so V hat is, okay, let me not put that, it will confuse people a little bit. So V hat, let me not put, let me put new. So I want to form a new estimate of V hat. So what will I do? I will take V hat old plus some alpha times right, this will give me V hat new. So this is the classical stochastic averaging rule that we looked at. From very beginning we have been seeing stochastic averaging rule. I told you that almost everything that we will see later will get converted to a stochastic averaging rule, right. So this is a stochastic averaging version of what? Monte Carlo evaluation, right. This is Monte Carlo policy evaluation, this is stochastic averaging version of it, right. So you can think of this as old value, okay, that is target minus current, okay. So the target minus the current prediction, right, added to your old prediction gives me the new prediction, right, and this is some form of a error term, right. Okay, so I can make the rule, I can make this correct. And this is what we said was a stochastic averaging rule, right. So in the bandit case, then we showed you this alpha should be 1 by n, and or we can keep a constant alpha, all of those things we talked about, right. So this, all of you are on board with this expression. So this is essentially the incremental version of simple Monte Carlo estimator, right, without all the other complications I spoke about today. There is no important sampling, nothing. Okay, I have a policy phi, I am evaluating the policy phi, this is the estimator. Target is this, the expected value of GT, right. The target is an expected value of GT, but I do not know the expectation. Right? I don't know the expected value of GT. So all I have is a sample, right? One sample of this quantity of whose expectation I am taking, right? So I plug in that sample here instead of the target.
Actually, we don't have a sample of that. Right? We
Yeah.
only have one step involved.
No. I'm talking about Monte Carlo here. I'm not talking about. That's why I said. That's why I kept saying this is the incremental version of simple MC. Okay. So everybody on board. So this is MC, not TD. So everybody on board with that? Yes, no, maybe. Good. So now let us go look at this target fellow closely. Okay. So what is the target? It's GT, right? So what is GT going to look like? Right. So we will do the same trick that we did earlier. Correct? If I know the true value, and since I don't know the true value, I am going to write this as. Now can I plug this into this? If I want to, I mean, right. So now I can say that right. So everybody on board with that? Yes, no, maybe. So notice where the new is, where the old is, and where the t is and where the t plus 1 is. It's important. Okay, so remember it, right? So I don't want you to tell me later that you are using value at time t to form an estimated time t plus 1. Very careful. You are forming an estimated time t plus 1. That is why this is indicated new. Initially I wrote Vt and I erased it and wrote new because I wanted to make the distinction. Okay. So the value function estimate is new estimate, okay, but I am making it for the state I encountered at time t. Okay, and I am using the old value I had for the state I encountered at time t plus 1. Right. So this derivation clear, right? So what we did here is very simple, essentially the same trick that we used for deriving the Bellman updates, right? So the same trick I used here, except that I plugged it into, instead of plugging it into the original return equation, I plugged it into the Monte Carlo update, right? I used the same trick, plugged it into the Monte Carlo update, I get this expression. Okay. So if you think about it, this is exactly what I wrote here in the picture, right? So I am going to update the value of this state, I will use the reward I get plus the value at this state. Okay. So a value a policy evaluation algorithm that uses this kind of an update for finding the value function, okay, is called a TD0 algorithm, right. So, you should be able to write a whole algorithm around this and be able to implement it and all that, right. So, you start off with some arbitrary guess for the value function, you have a fixed policy pi, you start off with some guess for the value function, then you start generating trajectories, right. As you go along the trajectory, you keep updating the value function using this update. So, you come to the end of an episode, you go back, reset the state, but do not reset the value function, okay, reset the states and continue. Okay, so that is essentially what is going to happen. You could have all kinds of tricks you could use. You could have an optimistic initial value, right. You could do all kinds of different kinds of explorations on top of the basic policy, right. If you are going to use exploration on top of the basic policy, what you should be careful about? Huh? My God, this is a chapter. Yeah, this is a chapter 1 question. Should you or should you not?
If you update the policy, that is following change.
If you know, we are talking about valuation here. I am not talking about evaluation here. So I am not talking about control, right? In evaluation, you should not. But I am trying to evaluate a fixed policy. If you update over an exploratory action, you are evaluating a different policy, right? Over exploratory actions, you should not make any updates. Okay. So that is basically TD0, right. So we have done one algorithm now. This is the basic policy evaluation algorithm, right. So do people understand the concept of TD, what we are doing here? We are looking at things that is one step away and we are trying to update things, okay. So let us
Can you this function roll out while heuristic update? So while you are updating the heuristic, you are just looking one step.
see, that is what when you are doing the depth limited rollouts, right, in some sense you are doing something like this, right. So one way of thinking about depth limited rollouts is that right, when you are doing depth limited rollouts, that is what you are doing. So I am counting the reward until I reach a certain point in time, after that I am adding the value function, right. So that is exactly what you are doing there, right. So you can think of this as just one step rollout, not even so it is like I just take one step and immediately use the value function, right. So that is one way of thinking about it, but I am doing only one sample. In rollouts I would have done that multiple times, but here I am doing just one sample. We will come back and explore this question a little bit later, right. In the next chapter we will explore this question where we will explain why the 0 is there. Okay, there is a family of algorithms called TD lambda algorithms where we will actually look at this kind of having multiple step rewards and then having the value function. Okay, so we will talk about that next time. Yeah.
Why do we update v hat of st and not v hat of st plus 1?
Well, you did not ask me that question when we were doing Monte Carlo.
Here it seems more of this
No.
question.
No, I am asking you to think about what we did in the Monte Carlo case, right. So we started in some state S, right, we generated an entire trajectory and we used that to update this value. So instead of generating the entire trajectory, I am just substituting this GT with a biased sample, but I am still measuring the return starting from ST. Because I am not measuring the return from ST plus 1, right. I could update the value of ST plus 1 but not using this expression. I will have to use ST plus 2 here.
I am saying so use v hat of st to get an estimate of v hat of st plus 1.
No, how?
Then use RT plus 1.
No. Why am I getting a estimate of v hat of ST plus 1 from v hat of ST?
No, I am saying you already
See,
have
v hat of ST plus 1 if I do not have any loops in my state space, V hat of st plus 1 will not even have V hat of st in its expression. The only way V hat of st will enter into the expression for V hat of st plus 1 if you come back to st, right, but st is a is a time index random variable, so you will never come back to st.
I'm just trying, I mean maybe it's not exactly relevant, but I'm thinking of something like Kalman filter where you do it the other way instead of
Kalman filter, you are trying to predict what the next state is going to be, right. So here I am not doing that prediction, right. So if you want, you can write a Kalman filter like equation here to predict what the next state would be. What I am trying to predict here, what I am trying to learn here is the reward starting from this state. I am not trying to predict the next state. It is entirely possible for you to write an expression for st plus 1 in terms of st, but not V hat st plus 1 in terms of V hat st. Does that make sense? No, we'll talk. We can talk offline. Yeah. Right. Yeah. Let's talk. I actually had some other thought. We can talk about it later. Yeah. Anyway, so that's TD0. Right. So any other questions on TD0? Okay, good. So I'm going to talk a little bit about trying to make it a little bit clearer as to what the difference between Monte Carlo and TD methods would give you, right. So we'll start off with a very simple data set, right. So I'm going to give you and that's the terminal state after that, right. So it's a sequence of states and rewards that you have observed. Let's assume the policy is very dumb policy, okay, because I am doing evaluation, right. The policy is fixed, I don't have to worry about the actions. So whatever is the policy, right, I just observe the sequence of states and rewards, right. So what is the value of A? What is the value of B? If I use Monte Carlo, let's say I use first visit Monte Carlo, let's keep things simple. Okay, I use first visit Monte Carlo. So what is the value of A, what is the value of B? Or let me make things even simpler. Let's have no first visit, every visit business. So what's the value of A?
Because the last one.
It's not critical for our example, so we'll just keep coming one. 4 by 3. Right? What about B? Sorry, yeah. Okay, I'll make a. Let's not have a 7 anywhere. Okay. Okay, so this is essentially a Monte Carlo estimate. Did I make a mistake here? Hey, sorry guys, I made a mistake in the number. I just cooked up some numbers and just realized now both Monte Carlo and TD will give you the same answers. So I need to give you a set of numbers where Monte Carlo and TD will give you different answers. Okay. correct? It's Monte Carlo, correct? V of A is 1 plus 2 by 3, so 1. B is 3 by 6, this is 1 by 2. Okay, so what will be the values estimated by TD? So essentially what you have to do is you have to keep updating this rule repeatedly till you converge. Okay, I am not that cruel. Okay, what you can show, which we will not show, but what you can show is that TD has this amazing property that you are applying that rule incrementally, but it computes the value function by implicitly constructing a Markov process, right. So, if you think about it, every time I will go from A to B, right. So, whenever I update the value of A, I will use the value of B. So, in some sense I am implicitly encoding that transition into my updation. So, it essentially it look like something like this. So, A go to B and B will go to a terminal state. We can see that, right, it's with probability 1 all of these transitions will happen, right. What is the reward for going from A to B? Okay, the reward is 2 by 3, the probability is 1, right, like what, that is expected reward, right, I am just removing. So, what is the reward from going from B to the terminal state? Right. So, now the value function that the TD update will converge to is the value function of A and B in this MDP or in this Markov chain, right. So, what is the value of B in this Markov chain? That won't change. Okay, here is the important interesting part. What is the value of A in this Markov chain? It is the immediate reward plus gamma times value of B, at gamma is 1. Huh? Seven by what? 6. Yeah, people accept this, right. So, what is the value of A is the immediate reward plus the value of the next state, right. So, that is the Bellman equation. So, the immediate reward is 2 by 3, the value of the next state turns out to be half in this case, which we already computed, right. So, 7 by 6. So, it came to a different answer than Monte Carlo, right. Monte Carlo gave me 1.5, TD is giving me 7 by 6.5. Which is the right answer? So, you see why TD tells me it is 7 by 6? See, whenever A occurred before B, right, B is been very unrewarding, right, only 1 out of the 3 times B gave me a 1, but the other times B occurred it had been very rewarding, twice it gave me a 1 and once it gave me a 0. Okay. So, what TD methods assume implicitly is that the whole system is Markov. So, regardless of how I came to B, when I go out from B I am going to get that expected reward of half, right. But it so happened that the few samples I drew from A turned out to be a bad sample for B, right. When I do the Monte Carlo estimates I am getting a lower value for A because of that. I do not take into account the structure, right. The structure is from A I go to B and then I go to the terminal state, and what TD methods assume is, okay, from B if you go to the terminal state, this is the reward you are going to get, and therefore from A if you go to B, then you will get whatever reward you will get from going from B to the terminal state. It makes that very strong Markovian assumption, right, and because it solves for this Markov chain. Okay. So now let me go back and ask you, which is the right answer? Thank you. Yeah, finally somebody said it depends. Yeah, depends on the problem, right. It turns out that what Monte Carlo methods are doing is essentially trying to minimize the prediction error, right, between this particular set of samples that you have drawn, the returns computed according to these samples alone, right. Going back to the definition of return, okay, it is actually minimizing the squared error between the value function you get and the return that you get from this, right. It is just trying to minimize the squared error from the fixed set of samples that you get, right. So what do TD methods do on the other hand is they form what are called a certainty equivalence model. Okay. So people in control theory probably understand this better. So there is something called the certainty equivalence model, which essentially is the model that best explains the data that you have seen so far under certain assumptions. Okay. So under certain assumptions you can assume that this model is equivalent to the system that generated the data that you have seen so far. Right. In this case we are making a very strong Markovian assumption, right, and what TD methods try to do is try to make the prediction according to the certainty equivalence model, right, trying to minimize the error between the value function in the certainty equivalence model and the predictions you are making here, right. So they are optimizing very different objective functions. Given an infinite amount of data drawn from a truly Markovian system, right, both will converge to the same answer. But given a finite amount of data, right, this will converge to the minimizer of the squared error, this will converge to whatever is the Markov model you can form with that limited data. Okay, this need not be the right model, this need not be the model that gave rise to the data, right. Given the limited data, this is the best you can do, that is all you can say, we are saying here. Given this data, what is the model you can form, it will converge to that, right. Whether this is the right answer or that is the right answer given a limited amount of data depends on what kind of application you are looking at, right. On the other hand, since the Monte Carlo methods make a less of an assumption about Markovianness, if you suspect that your system is not very Markov, okay, then do not use TD methods, you are better off, probably better off using Monte Carlo kind of methods, okay. But remember, I told you that if you use the notion of a value function, already you are making an assumption about Markovianness, right. Otherwise you should be using values of histories, right, you should not be using values of states. If you are already using values of states, you are making a Markovian assumption, but that is okay, right, in some sense, provided the reward estimates you are making since then, right, you take care of the Markovianness, non-Markovianness there, okay, but still it is not correct, but at least it will be more robust to violations of the Markov assumptions, and as you can see very clearly from here, right, just going by the evidence of the trajectories I have given you, you should not think this is a Markov system, right. So whenever A happens, B seems to have a depressed outcome, right. Just by the evidence of the data here, you should not think it is a Markov system, but TD will just assume it is a Markov system and go ahead and do the updates, okay. So you see the difference between what TD does and Monte Carlo does, okay, great. So we will stop here, we will worry about TD control in the next class. Yeah.
Limited data MC will converge to?
MC will converge to the least square estimate of the returns predicted by the data.